What's the strangest thing humanity has found on the moon? It's not aliens, nor is it a secret base. It's something that, by all accounts, shouldn't be there at all. With the advent of new crewed lunar landers, this discovery has become more critical than ever.
It's been over half a century since the last Apollo astronauts set foot on the moon. In that time, no human has returned, but we've sent dozens of robotic probes. Some landed successfully, some flew by, and some were deliberately crashed into the surface just to see what kind of splash they'd make. In short, the moon is the most studied and manipulated celestial body in human history. Yet, even after decades of research, it remains shrouded in mystery. From the way it stores heat to how it conducts electricity and even the properties of its soil, there is still so much we don't know. It seems to be a universal rule: the more we study, the more questions we find. For instance, before we had samples of lunar regolith, we were full of expectations. But once the soil was returned to Earth, a series of discoveries of chemical traces that shouldn't exist left scientists scratching their heads for decades. You might think a major scientific discovery would change everything overnight, but the real process of science is incredibly slow. Sometimes a clue can be staring everyone in the face, yet no one is ready to believe it. This particular story begins in 1976, when the Soviet Union launched an unmanned probe called Luna 24. It was their final mission to dig up lunar soil. At the time, nobody paid it much attention. It wasn't the first mission of its kind, nor was it particularly large-scale. But it quietly accomplished something monumental. It drilled about 2 meters beneath the lunar surface, extracted a small core of regolith, and sent it back to Earth. The sample weighed only 170 grams, about the same as a baseball. It wasn't much, but within that narrow column of dust, something strange appeared: traces of water. About 0.1% of the sample contained water, and the deeper you analyzed the sample, the more water you found. This should have been a groundbreaking revelation. Instead, it was dismissed. Scientists assumed the water was contamination from Earth, perhaps from the lander or from equipment back in the lab. After all, the textbooks were clear: the moon was bone dry. Water was impossible. This wasn't the first time either. Similar hydrogen signals had been detected in the soil samples brought back by the American Apollo astronauts, but they too were written off as contamination. And so, these clues, which should have caused a scientific uproar, were relegated to the footnotes of lab reports, gathering dust for decades. It wasn't until the turn of the century that scientists began to look back and wonder, did we miss something important? But by the time we were ready to take another look, the moon was prepared to present us with even more puzzles. If you were to stand on the rim of certain craters at the moon's poles, you would witness an almost unnatural sight, not because of what is there, but because of what isn't: light. You'd be looking into a permanent shadow that hasn't moved for billions of years. These areas are known as permanently shadowed regions. They exist because the moon stands nearly straight up, with an axial tilt of only about 1.5 degrees. This means that when sunlight hits the poles, it skims across the surface at a very low angle. The deep, vast craters prevent any sunlight from ever reaching their floors. These spots have likely never seen a single ray of sunlight in the entire history of the solar system. They are not just dark, they are brutally cold, with the coldest spots dipping below -240 degrees Celsius, 400 F. That's colder than the surface of distant Pluto, making them some of the coldest places in the entire solar system. In the 1990s, scientists began to theorize, if comets or asteroids carrying water had once struck the moon, could some of that water vapor have drifted into these craters, frozen solid, and remained there ever since? The idea caught fire. It meant the moon might not be a dead rock, but a repository of resources, a potential fueling station for the future. From that point on, all eyes turned to the lunar poles. Looking from Earth was no longer enough. We had to get a closer look. The problem is, these most promising locations are also the most difficult to reach. The terrain is treacherous, and there is no light, rendering solar panels useless. But the temptation was too great. What if there really was ice? And so, wave after wave of exploratory missions were launched with a single goal: to find definitive proof. This is when things started to get strange again. Scientists suspected there was ice, so the next logical step was to send a scout. But landing directly was too risky, so the first few missions were orbiters. The first was NASA's Clementine in 1994. Its primary goal wasn't to find water, but to map most of the lunar surface. It confirmed the existence of large, permanently shadowed craters at the South Pole, but it lacked the right instruments to confirm if there was ice inside them. Then, in 1998, NASA launched the Lunar Prospector, this time with the specific goal of finding water. It scanned the moon with a special instrument and detected massive hydrogen signals at both poles, especially in the shadowed regions. Scientists were ecstatic. Theoretical estimates suggested the ice reserves could be in the tens or even hundreds of millions of tons. This wasn't just a puddle, it was a discovery that could change the future of space exploration. But then came another problem. Detecting hydrogen isn't the same as detecting water. The hydrogen could be part of the hydroxyl radical or locked away in minerals. The instrument couldn't tell the difference. It could only tell us there was a hydrogen-bearing substance there, but not whether it was part of water ice. Even if it was water, an orbiter couldn't see it directly. This was far from concrete evidence. The scientific community was once again left scratching its head. They had data and clues, but no final confirmation. It was as if the moon was telling us it had a treasure, but wouldn't let us look inside the chest. So scientists devised a new plan. If we can't see what's in the shadows from above, let's just blow it out into the sunlight. You heard that right. They decided to crash something into the moon. The logic was simple. If ice is hidden at the bottom of a crater and I can't see it, I'll hit it with something hard, blast the contents out into a plume, and then I'll be able to see what's in it when the debris flies into the sunlight. The method was crude, but it might just work. The first attempt came from the Lunar Prospector itself. After completing its mapping mission in 1999, it was deliberately crashed into a crater near the lunar South Pole. Unfortunately, the attempt failed. No water was detected, and the results were inconclusive. Some said the impact angle was wrong, others said they simply missed. 10 years after that failed attempt, in 2009, NASA's LC-CROSS, Lunar Crater Observation and Sensing Satellite, mission brought a breakthrough. This time, they came up with a masterstroke. The mission brought along its own battering ram, the spent upper stage of the rocket that carried it into space. First, it slammed this massive piece of metal into a crater near the South Pole called Cabeus. A few minutes later, the LC-CROSS satellite itself flew directly through the plume of debris created by the impact, analyzing it on the spot. This time, it worked. The instruments on board detected water vapor in the plume. This wasn't a hint, it was real, measurable water. Not only that, but they also found methane and ammonia. For the first time, humanity had tangible proof of water on the moon. Headlines around the world celebrated the discovery. Scientists popped champagne, feeling that this decades-long mystery had finally been solved. But soon, new questions arose. The impact worked, but how much water was actually there? Was it in solid blocks of ice, or was it mixed into the soil like a frozen slush? And most importantly, how easy would it be to dig up? LCROSS had given us an answer, but it had also been destroyed in the process, unable to provide more information. We knew there was water at that one spot, but a complete picture of the moon remained a mystery. For the longest time, the thinking was straightforward. If the moon had water, it had to be hidden in the coldest, darkest, permanently shadowed regions. These places act as natural deep freezes where ice could survive for billions of years. The logic was sound. But the moon always has a new trick up its sleeve. Orbiters like NASA's Lunar Reconnaissance Orbiter, LRO, which has been circling the moon since 2009, and India's Chandrayaan-1 began to pick up faint signals of water molecules outside of these cosmic freezers on the sunlit surface of the moon. This discovery completely baffled everyone. Finding water in a place that gets direct sunlight, where daytime temperatures can soar above 100 degrees Celsius, 212 degrees, shouldn't that water have evaporated and disappeared eons ago? What was even more perplexing was what came next. Scientists found that these water signals weren't constant. They seemed to follow a daily schedule. Around high noon, when the sun was at its fiercest and the surface was hottest, the water signals would weaken or disappear entirely. But as evening approached and the ground cooled, the signals would return. What was happening? Was the moon sweating? Did it work up a sweat during the day and reabsorb it at night? This phenomenon was completely counterintuitive. The moon is a vacuum, with no atmosphere, no air pressure, and certainly no weather. On Earth, water evaporates and condenses to form clouds and rain, the water cycle. But how could a barren, airless world like the Moon have a water cycle? This was one of the greatest puzzles the Moon had ever thrown at us. So where was this water coming from? Scientists, scratching their heads, came up with a few possibilities. One theory is that it's delivered by cosmic visitors. Every day, countless micrometeorites, no bigger than dust particles, strike the Moon. They might carry a tiny bit of water themselves, or their impact could release water that's locked within the minerals of the lunar regolith. Another, more intriguing theory is that the sun is making it. The sun constantly blows out a stream of charged hydrogen particles, what we call the solar wind. When this wind hits the Moon, the hydrogen ions can collide with the oxygen in the lunar soil and synthesize water molecules right on the spot. Whatever its origin, this discovery was a game changer. It meant that we might not have to venture into the dark, cold, and incredibly difficult to access polar craters. Perhaps the entire surface of the Moon is coated with a thin, moist layer of water, if only we have the means to collect it. This suddenly expanded the potential locations for future lunar bases exponentially. This tantalizing possibility directly inspired the next generation of lunar missions. And so, in 2023, scientists from India took up the challenge to solve this ultimate riddle. The Chandrayaan-3 lander successfully touched down, and its target was the South Pole, the region scientists believed had the highest concentration of frozen water. This was humanity's first ever landing in this region. The world watched with bated breath, waiting for the Pragyan rover to send back news that it had found ice. The rover began its work, using lasers and X-rays to analyze the soil beneath it. The results? It found aluminum, iron, calcium, and titanium, but no hydrogen. No hydrogen meant no water. Everyone was stunned. Where was the water that the maps so clearly indicated? Had we been wrong all along? Or was the water buried too deep for the rover's small instruments to reach? Before anyone could figure it out, the 14-day-long lunar night descended. Temperatures plummeted to over 100 degrees Celsius, minus 150 Fahrenheit. Chandrayaan-3 couldn't survive the cold and went into a permanent sleep, leaving us with an even bigger mystery than before. However, Chandrayaan-3 did not perish in vain. Before it went silent, it unintentionally discovered a critical clue with one of its temperature probes. It measured the temperature of the lunar regolith and found that while the surface was scorching hot from the sun, around 60 degrees Celsius, 140 degrees Fahrenheit, just 8 centimeters, about 3 inches below the surface, the temperature dropped dramatically to negative 10 degrees Celsius, 14 degrees Celsius. This massive temperature difference meant one thing. The top layer of lunar soil is an incredibly effective insulator, like a thick thermal blanket. The heat from the outside simply can't penetrate it. This perfectly explains why the rover found nothing on the surface. The water ice was likely hidden just a few centimeters beneath this down jacket, safe and sound. It's likely not that there is no water, but that our shovels have been too short. So the question is no longer whether the Moon is dry, but whether our tools are sharp enough to dig properly. If this is true, then the next lander won't need to fly farther or see more clearly. It will just need a more powerful drill. For decades, the search for lunar water was seen as a scientific curiosity, a way to better understand the Moon's history, geology, and how water moves through the solar system. But that's no longer the main reason for our interest. Today, lunar water means something much more immediate, a launching pad for humanity's journey into the cosmos, and the cornerstone of future space bases. If we can find usable water on the Moon, enough to extract, purify, and store, it unlocks everything else. First, it makes long-term lunar missions possible. Water is heavy, and launching it from Earth is prohibitively expensive. Water delivered to the Moon is worth more than its weight in gold. But if astronauts can source it locally, they can dramatically reduce the supplies they need to carry. This water can be used for drinking, cooking, cleaning, or cooling equipment without relying on constant resupply from Earth. Second, water can be split into hydrogen and oxygen, the same fuel combination used by many modern rockets. If we can build a system to extract water ice and convert it into propellant, the Moon becomes more than just a destination. It becomes a gas station, a place where spacecraft can refuel before heading into deeper space, to Mars, the asteroids, or beyond. This changes the entire equation. Currently, every mission has to carry all of its fuel from the start. But establishing a resource base on the moon could lighten the load. Launching from the moon is also easier. Its gravity is only 1/6 that of Earth's, which means less energy, lower costs, and greater flexibility. A spacecraft launching from the moon wouldn't need a massive rocket, it would just need a push. Third, local water changes how we build. It can support closed-loop life support systems that recycle waste into usable resources. It could even help grow food. Some plants can grow in lunar soil under controlled conditions, but they still need water. If we find enough of it, future habitats might not have to depend entirely on resupply drops or hydroponics. This would be a pivotal development for the future of human space exploration. But while the potential is enormous, we still don't know how much water is available or how easy it is to get. All these fuel depots and missions beyond the moon are only possible if we can extract that water first. This brings us to the final problem. Despite so many missions, so much data, and so much optimism, the truth is, we still don't have a clear path forward. Every time we think we've figured out the moon, it throws something new at us, a contradictory reading, a missing signal, an unexpected result. This pattern has repeated itself time and again. We see strong hydrogen signals from orbit, but then find no hydrogen in the soil upon landing. We detect signs of water vapor in an impact plume, but see no frost, no ice sheets, no visible accumulations, even in craters that have never seen sunlight, places cold enough to preserve ice for billions of years. High-resolution cameras still haven't captured any clear, reflective surfaces that look like ice. Instead, we get ambiguity. Shallow probes come up empty. The water detected by instruments seems to vanish during the day. Rovers have driven across craters that were supposed to be filled with frozen material, only to find more dust. Even new technologies like the shadow cam, despite its ability to image the darkest places on the moon, have yet to reveal the kind of clear, reflective ice sheets scientists were hoping for. This raises an unsettling question. What if we've been wrong all along about how the moon stores water? What if the models need to be revised? Or worse, what if the water is there, but it's so thinly distributed, buried so deep, or so chemically bound to the soil that we are simply not equipped to get it? Of course, the optimistic view is that our tools, while precise, are still not good enough. Our orbiters are like eyes in the sky. They can see a wide area but can't touch the ground. Our landers and rovers are like outstretched fingertips. They can touch but can't dig deep. All our explorations so far have been like trying to scratch an itch through a boot. We always feel like we're just missing the mark. The spectral data sent back is full of riddles. It tells us there's hydrogen, but not whether it's in water or in rocks. It tells us a patch of ground is bright, but not whether that brightness comes from frost or from a particular type of mineral. But the word "give up" doesn't seem to be in the human vocabulary. On the contrary, the deeper the mystery, the more our curiosity is ignited. New missions are lining up, more powerful landers are being built, and all eyes are still fixed on that place where we firmly believe treasure is hidden. The next mission will likely carry a more advanced Loyang shovel, a tool with a deeper drill and a smarter extraction system. It won't be about probing anymore. It will be about once and for all piercing through that final layer of mystery to pull up a cold, solid handful of the future from beneath the insulating lunar soil. Of course, the moon might play another joke on us, revealing even more unsolved mysteries. But when our shovel finally does lift up that handful of a cold, solid future, a new era, even grander than the moon landing itself, will begin. At that moment, this blue planet beneath our feet will no longer be just the cradle of civilization, but the harbor from which we set sail for the stars.